All right, so 10-2 areas, trapezoids, rhombi, kites. Here is the formula for rhombuses. Actually, let's slide back first. This was on yesterday's PowerPoint, right? It's in today's PowerPoint. It's been total throughout the year through about 6 PowerPoints. It means it's important, okay? We need to know what an altitude is. And for trapezoids, we'll look at these altitudes over here, okay? Now, this thing here is an altitude no matter where I put it, as long as it's perpendicular between the two bases, right? Okay? Now, when we make the altitudes in trapezoids, you can put it there, but it's never useful there. Because a lot of times you're not going to know what the altitude is. And you're going to have to use Chapter 6, Chapter 7, Chapter 8 information to help you find out what the height of the trapezoid is. Does that make sense? So the best place to do that then, to place the altitude, is right there. Because what did it just create where my cursor is? Triangle. And from Chapter 6, Chapter 7, Chapter 8, you know a lot about triangles. Okay? So that can allow us maybe to use the Pythagorean theorem, such a right triangle, SOHCAHTOA, to end up finding unknown values that are necessary for a formula for finding the area of a trapezoid. Okay? Often, it's often useful if your trapezoid is not a right trapezoid, because a right trapezoid, you guys know what a right trapezoid looks like? I don't know if I can, I can't do that here. So a right trapezoid would look like this thing here, where we have a kind of a right angle right here. Does that make sense? Do you see? So this would be an altitude. Okay. There's no triangle on this side of the trapezoid, right? Okay. There's only one over here. But when we have trapezoids like this one, it's going to be useful to draw in both altitudes. Okay. Now I'll give you the formula. And I think it's a good idea as you're drawing these formulas, you guys, writing these out, to draw the pictures that accompany them, okay? Because some of your formulas are going to have, and this one's got B1, B2. We haven't seen that before. What are they talking about B1 and B2? Later on in this PowerPoint, probably tomorrow, we'll see rhombuses. It'll talk about D1 and D2. And maybe, after we put all our formulas together, and we go back and use that, okay, what did D1 stand for? What did D2 stand for? What was B1? What was B2? Having a picture is going to make it easy for you to realize what those things represent. Okay, so having that picture is useful, along with, obviously, the formula. So 1/2 H, B1 plus B2. That is your formula for finding the area of a trapezoid. Okay. Maybe something we already knew. Anybody already know that? No? Okay. That formula is created through the use of finding the area of a particular rectangle. So even though that doesn't look like the rectangle formula, B times H, that's exactly what that is. Okay? And so I'm going to prove with you visually how that formula comes out of a rectangle, okay, or is due to the fact of knowing a rectangle's formula for area. Everybody got that written down? All right, so when we try to figure out what this is, in this applet that's on my website, made it last year, you can mess around and change the trapezoid by moving A, B, and that little X down the bottom. So this will work for any trapezoid that we ever come across, okay? Whether it's regular, isosceles, right, whatever, doesn't matter, it's going to work, okay? First thing we have to do, though, is we have to come up with the midpoints of the legs. You guys remember doing that? Okay? And then we connected them. Remember doing that? Okay? And this was it was either the end of Chapter 4 or the beginning of Chapter 5. We talked about the mid-segment of a trapezoid, and this was the formula for finding the length of that dotted line. Okay? And we went through a proof of doing that. We went through the proof of, I think we put this on the 0, 0, put that point right there on 0, 0 on the X and Y axes. We found that coordinate. And then we worked through the distances of these things, and we found out that was an accurate statement. 1/2 B1 plus B2 is that distance. We can work through, just to prove it to you here real quick, That distance is 16. That distance is 49.05. So that's about 66-ish, right? A little bit less than 66, 65-ish. So this should be half of that. So it should be H2I should be about 33 something, 32, okay? I overestimated the 49 to 50, so then that 32.53 should be a little bit less than 33, okay? So that makes sense. Does that make sense to everybody? If we were to add the 16, the 49.05, add those together, divide by 2, you get 32.53, okay? So just want to remind ourselves of that fact, okay? So I'm actually going to remove that right now just because it creates clutter in the rest of the proof. The creation of this formula comes from taking those two altitudes, putting those altitudes in. And we can put them anywhere, right? As long as, by definition, an altitude goes from the line containing one base perpendicular to the line containing the other base. So as long as I have, let's say, that line there and that line there, as long as I take a distance that's between those two lines, isn't that distance, and it's perpendicular to both those lines, isn't that distance going to be the altitude? So if I take, let's say I take this altitude right here. Can I move it right there and it still be the altitude? Can I move it there and it still be the altitude? Okay, so I'm going to move it right there. I'm going to move it to that midpoint, so it intersects that midpoint. Okay? And I just want to prove to you, using distances real quick, that that distance right there is 16. That distance right there is 16. So I didn't change the height of the trapezoid, right? Okay. This one here is 16. I'm going to take that one on the right, and I'm going to move it as well. Guess what that distance is going to be? 16. So hopefully you see that it doesn't matter where those altitudes are, it's still the 16, it's still contributing to our formula the same way, right? Okay. Let me get rid of those 16s real quick. All right, so we move those altitudes out to intersect the midpoints. Now, what happens is that this is still a right angle where my cursor is. Okay. This angle here and that angle there are vertical. Okay. This side here and this side right here are congruent because that point right there, H, was a midpoint, right? Okay, capital H was a midpoint. So what we have here is two triangles that are congruent by angle, side. Does that make sense to everybody? Okay. And that's what it's saying here, show these triangles. Basically, this blue triangle here is congruent to this triangle where my cursor is. This green one is congruent to this one. Okay. Well, if I take that blue one and rotate it, when I rotate, is the area of this blue triangle the same as the area of that blue triangle? Yeah. Isometries preserve distances, therefore they preserve areas. And I do that. Once I reposition, basically I'm rotating and cutting and pasting that triangle that's on the bottom to right there. Is it okay? So I haven't deleted or gotten rid of any area. I've just repositioned it, right? Okay. Can I do the same thing over here on the right-hand side? Make sense? Okay. Now remember what we did here. This was an altitude right here, correct? This distance here, altitude. So isn't this a right angle where my cursor is? Isn't this a right angle where my cursor is? Okay. So when I rotate, didn't that become a right angle now? So right angle, right angle, right angle, right angle. What is that shape that I just created? A rectangle. What's the area formula for a rectangle? B times H. Okay? So area of this rectangle is B times H. Now, the H is the distance between, maybe, let's just use this top here, that side and that side. Wouldn't the H of that rectangle be the same H that existed for my trapezoid? Okay? So I'm going to leave it as H. Okay? Now B would be this distance here, or that distance there. Does that make sense to everybody? Now for my trapezoid, I don't know what those were. Okay? I do not know what those were. But what can you tell me a relationship about that altitude right there and that altitude right there? They're the same. And what'd you say? What'd you say? They're the same. What'd you say? Parallel. Okay? They're parallel. And one of the definitions that we use for parallelism was that the distance between two parallel lines never what? Changes. So those blue lines right there that are the bases are the same as maybe that line right there. Or maybe the same as that line right there. Or maybe the same as that line right there. What's that line right there called? It's the mid-segment, isn't it? So do you see how the base of my rectangle is 1/2 B1 plus B2 here? Okay, so if I replace this, okay, so for my trapezoid, this distance here is 1/2 B1 plus B2. And then to find the area of the rectangle, so that is providing that distance right there. That's 1/2 B1 plus B2. This distance here was the height of my trapezoid. So there's my formula. Does that make sense to everybody? Okay, so finding the area of a trapezoid, deriving, we call it deriving. Deriving that formula involves, we use rotations, isometries, understanding of that the area is not changed when we rotate. We use congruent triangles. I used angle side there. We use midpoints and mid-segments. And then some area formulas, right? A lot of stuff that we use that kind of tie together to provide this one formula. But ultimately, it's a formula that is generated by knowing what the area of a rectangle is. Okay? Now, am I ever going to ask you to reproduce that? No. But I'm a huge proponent of giving you formulas and telling you where they come from. Okay? I sat in classes all the time in high school and college, and they just throw out formulas at you. And you just take it for granted. Okay? If you take it for granted, there's going to be a situation at some point where you need to understand how that formula is created to address some of your problems. And if you don't know that, you're going to struggle. If I understand where that's coming from, and it's really the redistribution of areas to come up with that formula, I think it makes application of that formula so much easier later on. Okay? And in other aspects of math as well, that concept shows up. All right, so let's do something. We'll do 2 examples and we'll be done. Okay, so I want to find the exact area of this thing. I do not want a decimal, okay, because when we get a decimal or we approach this using a decimal, we circumvent or we go around a lot of potential algebra that we can get better at. So, as anything we do in math, we would like to kind of structure a plan, right? Kind of talk about what is governing the entire problem, the original problem. So they're asking me for area. So the formula for area for a trapezoid, you just wrote it down, is this: 1/2 H B1 plus B2. I would write that down. That governs the problem, and now there's missing parts, right? There's 3 things in there that I need. So I go through and I start filling in the things that I know. Do you know H? H is 7, right? Do you know B1? Okay, so you know an entire base. It could be 8. Okay? I mean, it doesn't matter. That could be B1 or it could be B2, right? But regardless, you know one of your bases. Do I know the other base? No. It's at least 13, right? But I don't know the other part of that 13. I don't know that right there. How can I find that, though? Yeah, math. Pythagorean theorem, right? Okay. So, if this is, let's just call this A. Can I say a squared plus 7 squared is equal to 11 squared? So a squared is going to be 121 minus 49. A squared is equal to 72. A is root 72. Okay? So we're getting to the point, guys, where we've been working on radicals. We've been working on special electrons. We've been working on all that stuff for a while. The hope is now that this is just stuff that can kind of flow quickly. Okay? What is the first square that divides 72? 9. Okay. So that would give me 9 and 8, right? Now what's the perfect square that divides 8? 4. So 9 and 4 should have divided 72, right? So what's 9 times 4? 36. So 36 is actually the biggest perfect square that will divide 72, right? You're not wrong by saying 9 and 4, or 9 and 8, and then breaking the 8 down to 4 and 2. That all works. But what's the square of 36? 6. So my A value here is 6 root 2. That's the other part of my base number 2, right? So this is what I was saying. If I wanted this in rounded to the 10th place or 100th place or whatever, I could type that in my calculator just like I see it. Same amount of parentheses and all that kind of stuff, and it's going to give me the exact value to 1 decimal place, 2 decimal place, 3 decimal places, whatever. But it circumvents the opportunity to get better at working with the distributive property, multiplying fractions, adding irrational numbers to rational numbers, and that kind of thing. So I'm going to ask a lot of times to leave your answers at exact values so that you practice that. Because you guys don't know who your algebra teacher next year is going to be, right? What if they're a person that comes in and assumes that you know all that stuff? Because those are Algebra 1 standards. Okay? Then we would be kind of in a precarious situation as Algebra 2 students, right? Okay? So let's kind of work through this order of operations and get better at this so that next year it's not an issue for us. I wanted some room here. If I'm going to go through order of operations, tells me to do parentheses first, right? Okay. Now we also, not only do we have order of operations here, but we have objects that are not like terms, right? We have some rational numbers. 8 and 13 are rational. 6 radical 2 is irrational. Only rational numbers work well with rational numbers, right? Through addition and subtraction. So I can only change this to 21 plus 6 radical 2. Okay? That's rational. That's irrational. They don't add together well. They don't divide, sorry. They don't add together well. They don't subtract together well. Okay? We can multiply them and divide them a little bit easier, but it's still not great. Okay? So now I'm going to run through the order of operations again, but now I've already done that. I've already expended that set of parentheses. There are no exponents. Now I just get multiply, divide, left to right as I see them, right? Now, I don't know what the word I'm looking for here, but collectively, the order of operations in other properties like the associative property and the commutative property are all kind of existing together at the same time, right? So even though you're trying to abide by the order of operations, you can still use commutative properties and associative properties to maybe make multiplication processes easier. I think those two, of the numbers that we have here, because essentially we have 3 numbers. We have that one, 1/2, we have 7, and we have this one, whatever that thing is. Okay, we have 3 numbers. Does it make sense that these two are better together than maybe 1/2 and this one? Or better than 7 and this one? Okay, because 1/2 and 7 are both what kind of numbers? Rational. So a rational times a rational is easier to do than a rational times an irrational. Okay? So I'm going to multiply those together. And it's a fraction times a fraction, right? So top times top. So 1 times 7, 2 times 1. And now I still have this. Now here's where, even though we wanted in the last step to multiply rational times rational, here we get to a situation where it's unavoidable. We have to multiply a rational times an irrational. Okay? But this is a quantity here, right? With quantities, do you, well, what is the operation you have to do? If I want to take that number times a quantity, what's the word you use? You distribute, okay? So I multiply those two, fraction times a fraction, right? So in the last class I said, right there is 3.5. And then I asked, okay, what's 3.5 times 21? And I was trying to urge them, okay, what is it, what is it, what is it? And they couldn't do it, okay? Under pressure, though, if I take 7 times 21, 7 times 2 is 14, 7 times 1 is 7, right? 2 times 1. You can come up with that so much faster than 3.5 times 21 in your head, okay? So that's distributing there. Now I've got to distribute to this, right? Okay? Same thing. If I ask you to take and multiply these, I'm going to take the 7 times the 6. Remember, multiplying radicals, you take the numbers out front and multiply them together. So it gives me positive 42, right? And then the numbers that are on the inside of the radicals, they multiply together. Is there a radical here with the 7? No. Could I put radical 1 there, though? Yeah. And that might make it more obvious. I take radical 1 times radical 2, and it gives me just radical 2. And then I've got 2 times 1 here, which is 2. All right. Now that is a better answer than as a decimal, but it's still not best, because what do you call that 2 and that 2 for these fractions? They are like, they're the same denominator, so they're common denominators. So can't I just turn this into 147 plus 42 radical 2 all over 2? Yeah. Okay. Or, if I want to leave this as 147 over 2, can I cancel those and give you what? What's 42 divided by 2? 21. Okay? So, in regards to writing your answers, and I'll set up questions so that it counts both of those. And I'm looking at the exact answer. I'm looking for 147 plus 42 radical 2 over 2, or 147 over 2 plus 21 or 21 radical 2. Okay? Because if I was going to use and ask for a decimal, you bypass all that work, which you might be like, yeah, that's what I want to do. But if you continually bypass something, let's say I'm playing basketball and I'm not very good at shooting free throws, but I always avoid the opportunity to shoot free throws. Am I going to get better at them? No. Okay? If I always avoid radicals, am I going to get better at them? No. If I always avoid fractions, am I going to get better at them? No. Okay? So that's kind of the reason I'm going to ask you to do those things. I know how your next couple classes are going to work and how they operate. You're going to need to be better at this stuff. Okay? I'll do one more. We'll find the area of that thing. I'll give you a minute to draw that picture. What did you just say? Months. Yes, meters. Huh?
Think with your head, not your brain.
Yeah. All right, so this is, I don't know if you can really see it, but this is a right angle right here. Okay? And if this is a trapezoid, then the top and bottom are parallel, so that's a right angle as well. Okay? So if I go area, 1/2 H B1 plus B2, right? Do you know what H is? Now, H is that distance R to Q, right? And nowhere in my problem do I have that. Do I have B1 plus B2?
Yeah.
What's B1 plus B2? 5 plus 7, okay? Now, if I don't find H, remember at the beginning of class where we said the best place to put your altitude if you need to find it? Is right there, so you create triangles. What kind of triangle did we just create?
3069.
3069. Now, what's think about this 3069 is that we still don't have no values. Okay? But you do, but just hidden. What kind of figure, if it's the right angle here, what kind of figure is this?
Rectangle.
Rectangle. Bare minimum, it's a rectangle. Okay, now it could be a square, but I think we're going to find out that's just a rectangle here. What do you know about opposite sides of a rectangle? They're parallel and they're what? Congruent. So what is that distance right there? 5. Making that 2, which is the side that's across from 30 degrees, making this altitude 2 radical 3. So does that prove to you that that was a rectangle and not a square? Okay. Because radical 3 is about 1.7. 2 times 1.7 is not 5. Okay. But that is your altitude though, right? Okay. So that goes right here. 2 radical 3. Now let's think about this. Even though I write that in its own set of parentheses here, what this means is you have 1/2, a rational number, times 2, times radical 3, times 12, right? Rational, rational, irrational, rational. If I'm going to multiply all those together, and the order doesn't matter, which ones work the best together? Rational. So let's take the 12 times the 2. What's that give me? 12 times the 2. Yeah, 24. I was thinking 1/2 for some reason. So 12 times 2 is 24. What's half of 24? 12. In any order that I multiply that number, that one, and that one, I get 12, right? 1/2 times 2, what's that? 1 times the 12 then would be 12, right? That's what I was thinking when I asked the question, but I asked it wrong. So now I've got those 3 together give me 12, and now I've got this irrational. So don't I have to just multiply that? And now that is the implied multiplication. You're taking a rational number 12, irrational number radical 3, and you leave it that way. And that gives me the area then of that trapezoid. Yes? Yes. But when we say they cancel out, because it's all multiplication, they go to 1, and they're still contributing, but they multiply by 1. It's a multiplicative identity, so it doesn't change anything. There are situations where eventually, if there's a plus sign between the 1/2 times 2 and the 3, or radical 3 and 12, I don't want them just to disappear. Does that make sense? And when people say cancel, I think they just vanish. So your homework tonight, guys, 10.2 Math Excel. You're only going to be able to do about half of it. The other half is kites and rhombuses, which we'll talk about tomorrow. So that assignment's not going to be due until Thursday.